Okay. So now, okay, so let's see. Now let's look at the, so this is a just 4.2. We are just done with the 4.2. Now it's, let's say, 4.15. Okay, let's take a look at the 4.15. Okay, so the distal signature, right, provides the data integrity, and the MAC provide for the data integrity. Yes, both of them actually provide the data integrity. So what does a signature also provide? Why does a signature also provide a non-repudiation while MAC does not? Okay, and so please think about it. Okay. Okay, you know what? Let's just do 4.15. Actually, do the 4.15. Let's just do one problem, and the 4.37. You know what? Let's just, okay. You know what? Let's just do 4.37 because it's 4.37. It's basically, but the same question actually. Okay, the same thing. So let's look at the 4.37. So in the same, pretty much same problem. And just like I said, okay, oh, by the way, I want you to also do 4.35. So your answer just okay, and then please do 4.36. And this is really easy problem. You don't really need my help. And just be brief. Okay. So the 4.36 is define the non-repudiation. So please define it. And then given an example, different from the one given in this textbook where the non-repudiation is critical. Think about it, like, you know what? So be brief. So just come up with an example, right? Or the scenario where the non-repudiation is critical. Think about it. So this 36 is kind of, that's, you don't really need my help, right? And the 35, digital signature, right? It's not a digital certificate, it's digital signature. And then how and why those provide the integrity, and then how and why digital signature provide non-repudiations. Okay, so so I want to, like, for example, so where is my OneNote? Okay, so 4.35, right? So it's about the distal what signature, right? So for example, if the Alice, you know, create like her distal signature, right? And then what? So let's say there is a message M, and if he wants to create her, basically if she wants to sign this, right? The host, she can do what? M, and then what? This means the signs, right? Signs with a private key. This is important, right? Square means a private. Sign the message M with at least what? Private key, right? So this is how, so the she signs the message M, right? So that's a digital signature. So it explains why the how and digital signature can, why is integrity and why non-repudiations. Okay, I think you can just be brief. You know, don't. So for the 35, I mean it's a simple problem, right? So just don't write any wrong. Just be concise. Okay. Now the next one. So the 37 is I think it's the last problem. The digital signature of the MAC can be used to provide cryptographic integrity check, right? So A, suppose that Alice and Bob wants to use crypto integrity check. Which would you recommend that they use, MAC or digital signature Y, right? Suppose that Alice and Bob requires the cryptographic integrity check and also non-repudiation. Which would we recommend that Alice and Bob use, MAC or, okay, so think about it. But for the part A, so by the way, you guys hopefully, I mean, I already talked about this in my lecture, but let's just review, okay? Let's just review the, I think it's chapter, yeah. We talk about the MAC, right? MAC. So the MAC is called a message authentication code. And the MAC is computed as a CVC residue, right? So basically, the MAC is the so just please watch my video tutorial. I think I already explained this on my video in my lectures, and then my video lecture was, of course, I uploaded my video lecture on MAC. So please watch that video tutorial on the MAC. But the idea about the MAC is basically they use a symmetric key, right? And then they use the key, right? I mean, you don't have to really know the details, right? Only thing that you need to know about the MAC is what? I mean, to solve this problem, you don't really need all this detail. And just like I promised that I'm not going to use any math, right? So you don't really need any of this math. It's just, you should know the just concept, and that's it. Where's my OneNote? Okay, so let's just briefly talk about the MAC. So so basically the 4.37, right? It's comparing the MAC versus the digital signature. And one of the important property that the digital signature can achieve is integrity, right? It's one of them. And of course, for the MAC also can achieve the integrity, right? But how the MAC can be computed, right? You don't have to know all the details, right? The MAC is basically, let's say, let's say for Alice, right? If Alice wants to create the MAC from the message M, right? She goes to that, the CVC, block, whatever that, complicated procedure, right? But eventually, from this message M, she is able to, read the message M, and then a shared key. Okay, so this is what symmetric key, right? Or the shared key, same thing. So you can think, okay, let's say, so MAC is you can think a message digest. Actually, it's a code, right? That, let's say, this is a value, and then some functions. I'll call the MAC functions, whatever. Okay, I'm just making up, by the way. And then you put the M. Okay, so this is. So let's say this is like MAC functions, and then MAC functions, you put the message M, and then what? You put the shared key. So this is a symmetric key, by the way, right? This is a symmetric key, and then you get the MAC value, right? So that's you can use this MAC value to achieve the integrity, right? So basically, Alice sends a Bob that message M and then this MAC value, right? And then Bob need to go through the verification process, right? So please watch my video tutorial. And that's how the Bob can verify this integrity, right? And for the digital signature is what? Of course, using the asymmetric encryptions, right? And then the Alice sends a Bob and the message, right? And then H of M, and then her signature, right? And then Bob has the verification process. I'm going to skip this. I already explained this many times. So Bob goes through this verification process, and then finally, if the verification is successful, then we know that this M has not been modified, right? Or during the transit. So that's integrity, right? So now, if you look at the problem, problem A, suppose that Alice and Bob wants to use the cryptography. Which would you recommend that they're using? So do you recommend that they should use a MAC or the digital signature? Okay, and the answer is, where is the okay, so for the integrity checking, I mean, you know what, actually there's not much difference. They can use the MAC or they can use the signature, right? You know what, for the problem A, let me just change the problem. So don't just solve the problem A. So problem A is what? Let me just change the problem. Let's say, can both the MAC and the signature, right? Digital signature, provide the what? Integrity, right? What is the answer? Yes or no? Anyone?
Yes.
Yes. So the yes is ends, and then show how briefly. Okay. So let me just change the problem A. So can both MAC and digital signature provide integrity? Yes. And then show me how. Okay. So that's the problem A. Okay. So don't do the original problem. Please just do this. So basically this meaning, I want you to compare a MAC with digital signature. So in the comparison, the goal, yes, goal is integrity, right? Yes, both can achieve the integrity, but the way they do this verification process is different, right? Because this one, so comparing means that this one use what? The first comparison is this one use a symmetric key, and versus this one use what? Asymmetric, right? And it's kind of different, right? The verification process. So that's the part A. And the part B is let's take a look at the part B. Suppose that Alice Bob requires a cryptographic integrity check. Would you recommend that Alice and use the MAC or digital signature, okay? Okay, so in terms of non-repudiations, so let me change the problem B a little bit. In terms of repudiation, right? Like, if the goal is what? Achieving the non-repudiations, do you recommend using the MAC or the digital signature? Which one? Any volunteer?
Digital signature.
Digital signature, thank you. The MAC cannot achieve non-repudiations, and please explain why. Just briefly. Okay.
Digital signature.
Okay, please don't. Okay, so don't tell me the answer. So please explain why briefly. I mean, this is a simple question. Okay, so I'm good. So I'm done. So that's the chapter 4. I'm done with the chapter 4 pretty much. Exercise problem. So any question? Okay, so the thing is, for the 4.17s, so please you do a part A and part B, but you know that I changed the problems a little bit, right?
Professor, should we disregard the homework from the previous week? That's 4.1, 4.15, and 4.1.
Oh, you already did?
Yeah.
Ugh. Because 4.15 is related to 4.37, so it's fine. Okay, 4.19. Okay.
I mean, for everyone else who didn't do that,
Okay, hold on.
they need to be doing 4.15.
Okay, 4.19 is I'll use the extra credit. However, okay, okay, so I give you extra points if you do 4.19. I mean, what I mean by extra credit is if you, let's say if your grade is 95, right? Without 4.19, and I give you 100, for example, right? I give you extra, let's say 5 points. You know what? Actually, it's more than 5 points. It's, if you give me the correct answer, I give you a 10, but I don't recommend anyone do 4.19. So extra credit 10 points. But for example, okay, so by the way, extra credits 10 points. It's very challenging problem, by the way. It's very challenging. So that's why I kind of on purpose I decide to skip. But I cannot give you, for example, if your score is already 100, I cannot give you any score more than 100. I'm sorry. But if you get 90, yes, you'll get 100. And if you get 95, you'll get 100. But not more than 100. But it's challenging problem. It's worthwhile. Yeah, it's great problem actually. But I don't want to talk about it. And I don't recommend, if you don't have a time, please don't do it. It's a long problem actually. And but it's a good problem. And as you can see, none of them requires any math, just pure concept. Only thing that we probably need to do is use the notations, right? Okay, so any question? Okay, so I'm start recording my lecture.